Welcome. This is one that's going to focus on part 3, which is the last of our special senses, hearing and balance, equilibrium. So both the structures for hearing and balance are here within the ear. They do respond to separate stimuli and are activated independently. Both hearing and balance use mechanoreceptors that are going to respond to a couple different, again, separate stimuli, but mechanoreceptors. You can see the external and middle ear only are part of or only play a role in hearing, whereas the inner ear here, the labyrinth, has the apparatus for both hearing and equilibrium. So we've got, if we look at kind of just ear anatomy, right, we've got the lobe of the ear leading into the ear canal, into the eardrum, which then connects to the auditory ossicles in the middle ear, that then connect to the cochlea, which contains the apparatus for hearing, and the vestibular apparatus, which consists of these semicircular canals, and the vestibule, which contain our organs for balance or equilibrium. So if we look inside the cochlea, you can see it is this kind of snail shell shape, and if you were to look at a cross section, you can see here all of our kind of cochlear ducts and this kind of circular structure inside that we generally refer to here as the spiral organ, because this is the important bit right here in the cochlear duct, where kind of all the magic happens in terms of transducing sound into neural signals. So if we zoom in there on the spiral organ, or the organ of Corti, you'll see here's the basilar membrane, which separates the cochlear duct from the other kind of structure here, the other kind of fluid-filled area, the scala tympani and the scala vestibuli. These are kind of the two upper chambers, and then the scala media, or the cochlear duct, is here, and it's this basilar membrane at the bottom of the spiral organ that separates the cochlear duct from the other chamber here. So here's again basilar membrane. Here's your cochlear nerve. You can see here's your hair cells. So these are the mechanoreceptors. They have what we call stereocilia that respond, to bending. And then we have the tectorial membrane, which kind of overlays the hair cells. And then, of course, we usually have some supporting cells as well that kind of play accessory roles. But the hair cells and the stereocilia are what are actually responsible for sound transduction. So when we talk about sound, we kind of have to just kind of get some basic physics out of the way. For our hearing apparatus to work, for most of us, unless we're underwater, the sound waves are traveling in the air. Well, we have inside our inner ear fluid, and so the sound waves go from being in the air to in the fluid, and then those hair cells, those stereocilia, are mechanoreceptors that bend a certain way, and depending on which way they bend, we get a neural impulse kind of being sent to your brain. But for some basic physics of sound, you can think of sound as a pressure disturbance. Areas of high pressure and areas of low pressure, creating this kind of wave-like effect. Sound is usually produced by vibration. That's why the tuning forks worked in the lab. You can smack the tuning fork vibrates, and you get this alternating high and low pressure that then gets propagated, promulgated, carried by the molecules of the air or the molecules of the water. Sound radiates outward in all directions. It's not unidirectional. It's kind of all directional. And because it does kind of travel in waves, we can get a wavelength frequency and amplitude, and all of those different properties of sound will give us some information about the sound. So here's your tuning fork, and you can see it's radiating outward in all directions. It's not just moving behind it or in front of it. It's going outward in all directions from the tuning fork. And you can see we get these areas of high pressure and low pressure, high pressure, low pressure. The area of high pressure, the molecules get really compressed. The area of low pressure, then the molecules aren't really compressed. So the high pressure areas are the crests of the waves. The low pressure areas are the trough of the waves. And so you can see from wave to wave is wavelength. The height of the waves is then amplitude, and kind of how many waves per unit time is our frequency. And both the wavelength, the amplitude, and the frequency tell us some information about the sound. Frequency is what we think of as pitch. So high frequency waves, like you see here in red, that tend to be very short wavelength waves, that's what we think of as high-pitched sounds, or that's what our brain perceives as high-pitched sound. Low frequency, kind of long wavelength waves are what we think of as low frequency or low-pitch sounds. Best example I can think of is my tiny little dog, neighbor's dog across the street, a little tiny white dog. He has a very high-pitched bark. The waves coming out of his barks have a very high frequency, very short wavelength. My brother's Great Dane, that I'm kind of permanently dog sitting, has a very, very deep bark. So the sound waves created by her barking are very low frequency, long wavelength, so very low in pitch. Our hearing is about 20 to 20,000 hertz. We do measure frequency in hertz, although our best range of hearing is about 1,500 to 4,000 hertz. Anything less than 1,500, we're not so good with. Anything greater than 4,000, we can hear it, but not quite as well. And kind of one of the interesting things is that as we age, we tend to lose the high-pitched sounds first. So somebody who's 15 actually has a better range of hearing than somebody who is, say, 65. There would be frequencies of waves that the 15-year-old could hear that the 65-year-old could not. So that perception of those different frequencies is what we think of as the pitch of the sound. Now, generally when we think of sound, we're not usually getting just a single frequency. Kind of like with smell, one smell is really a whole bunch of odorants. Well, most sound that we think of as the sound of a violin is really a whole bunch of different frequencies kind of merging together. Now, when you guys did and used the tuning forks, that is just one single frequency. And that's why we could label the tuning forks with a specific frequency. But really, when you were to listen to somebody's voice, or to listen to a symphony, or to even listen to my dog's bark, you're really getting a much richer, more complex sound that's really comprised of many different frequencies, not just a single frequency, as is the case with the tuning fork. Amplitude of the waves is interpreted as loudness. So high amplitude waves are loud sounds. Low amplitude waves are very soft sound. We measure loudness in decibels. Our range for hearing is 0 to 120 decibels. A normal conversation is about 50 decibels. That can kind of give you a kind of good starting point. Anything less than that, you're going to be softer. Maybe you're using your indoor voice. And anything above 50 decibels would be somebody speaking louder, or obviously like I love rock concert, they're pretty loud. Over 120 decibels, you can actually cause damage to your ear. It can be quite painful, and if you have kind of prolonged exposure, not just once in a while, but constant, think about maybe working a jackhammer, anything that kind of continuous exposure to a sound over 90 decibels can absolutely result in hearing loss. That's why your parents maybe have told you that you shouldn't play your music so loud on your headphones. I don't really listen to that either. I like my music loud. So let's talk about how this works. How do we get sound waves in air to become neural signals? Well, the ear is incredibly well suited for this task. So the external ear, the pinna, basically acts like a big giant funnel, which then takes these waves and funnels them right into the acoustic meatus and then allows them to, at the same frequency as they were here, strike the tympanic membrane or the eardrum. The tympanic membrane then vibrates at the same frequency as the sound waves. That then sets the auditory ossicles vibrating. They actually amplify and increase not the frequency of the vibration, but just the general kind of pressure of the waves. These waves, these pressure waves, these sound waves, then basically the stapes acts like a piston, kind of pushing against the oval window here, and you can see here we've taken the cochlea and we've kind of unfurled it, as it were, and you can see here's the cochlear duct. Remember, the spiral organ is inside here, and then but the stapes presents and presses against the oval window here, and this is what then, now since we're in the perilymph, in the vestibuli kind of duct, we have now waves in fluid. So we go from the sound waves in the air to sound waves in the fluid. If the frequency is kind of below something that we can hear, they continue kind of out what we call the helicotrema, which is the end point of the snail shell if you unfurl it, and they never actually excite any hair cells. If they are within our hearing range, then these sound waves, these now fluid waves, basically move the basilar membrane, and when the basilar membrane moves, when it's pushed on by these sound waves, that then activates the spiral organ. And so if we look at that, here's the basilar membrane, and you can see here are our stereocilia on the hip. Sorry, that's my computer having a spaz. Okay, interesting. Wants to open a file that I already have open, but sure. You can see here is what the basilar membrane and the stereocilia, look like when it's not being kind of activated. You can see the tectorial membrane is on top here, and the stereocilia are kind of mostly upright. We're getting a little bit of neurotransmitter, so maybe a little bit of depolarization, but not really a whole lot going on in terms of our cochlear nerve. But when let me go back here for a second. When the pressure waves kind of disturb the basilar membrane, I'm going to go back one more time. When this basilar membrane kind of gets pushed by the sound waves, then the stereocilia up here get bent against the tectorial membrane. And that's what we're seeing back here. If we go back to here's our tectorial membrane, and you can see when, kind of depending on which way the stereocilia bend, we get cation channels opening, and that depolarizes the receptor cell, and we get neurotransmitter being released to the cochlear nerve, and we get action potentials if we have enough of it. And so it's that bending of the stereocilia that really opens these cation channels and depolarizes our cells. And of course, if we get enough neurotransmitter, then we get an action potential. Once we have an action potential in the cochlear nerve, then we can travel up to the brain and actually hear a specific sound. If we follow that pathway, you can see here is the cochlear nerve. So here's our first order sensory neuron. The cell bodies for the cochlear nerve are actually here in the spiral ganglion. The cochlear nerve, here's the vestibular part of that. Then synapse with a second order neuron, which takes it from the cochlear nuclei to another part of the brainstem, the olivary nuclei, where they will then synapse with a third order neuron, which takes it up the brainstem to the reflex center in the inferior colliculus, and then we got 1, 2, 3. A fourth order neuron goes from the inferior colliculus to the thalamus, and then a fifth order neuron goes from the thalamus to the auditory cortex in the temporal lobe. And that's what we're seeing here. So a pretty complicated pathway, 5 neurons as opposed to 1 or 2 or 3. In terms of kind of different bits of processing in terms of sound, loudness is mostly about the frequency of the action potentials. So again, this is this magnitude estimation that we can do. We get more action potentials when the hair cells themselves have a larger deflection. If they bend more, we get more release of neurotransmitter, which results in an increase in the frequency of action potentials. And that is then interpreted as a louder sound, whereas a softer sound would result in a smaller bending of the stereocilia, less neurotransmitter, and less frequent action potentials. We can localize sound quite well based on primarily the kind of intensity and timing of when the sound waves reach the ears. If, say, for instance, you have a sound that's on your right side, it's going to hit your right ear before it hits your left ear, and so your brain has an easier time saying, hey, that sound is on the right side of my body. Now, if the sound were coming from directly in front of you or directly behind you, then the sound waves would reach both ears simultaneously, and your brain would have a harder time determining the source of that particular sound. Pitch is determined by which of the hair cells within which part of the spiral organ, or really which spiral organ, are deflected. So again, if we unfurl our cochlea, you'll see that the basilar membrane is not kind of the same throughout. At the base, the hair cells are much shorter and much stiffer, whereas if we go to the helicotrema, the apex, the fibers are kind of much longer and floppy, for lack of a better word. So low frequency, they tend to not travel, they tend to not affect these kind of really short fibers at the base, but they can travel really long distances in the fluid. And so they tend to depress the basilar membrane much closer to the helicotrema, or the apex of the cochlea. And so when this kind of further part of the basilar membrane is depressed or deflected, bent, take your pick, then your brain says, oh, that's a low frequency sound. Conversely, high frequency sounds, they can't travel as far in fluids, and so they tend to bend the basilar membrane much closer to the oval window, and your brain then would then interpret that as a high-pitched sound when those particular hair cells are moved, as opposed to here. And you can see kind of mid-frequency sounds are, shockingly enough, right in the middle. So that's why frequency, low frequency sounds and high frequency sounds do appear different, because they are activating different parts, different spiral organs at different parts of, along kind of the length of the cochlea. Now again, please remember that this is something that's all kind of spiraled in. We're just kind of showing it out here as a solid line for kind of ease of understanding. So that's it for sound. Let's talk about equilibrium, which is now also here in the inner ear. So remember, outer and middle ear is just for sound. All of the organs for balance are here, not in the cochlea, but in what we call the vestibular apparatus. Now, the vestibular apparatus consists of two parts. The vestibule, which is this part here. The vestibule contains the utricle and the stachule, that both contain the sense organ, the macula or maculae, and they look at what we call static equilibrium, really relating mostly to head position. Now, the semicircular canals, all of these are filled with fluid. Their sense organ is called an ampulla, or an ampullae plural, and they look at what we call dynamic equilibrium, mostly about movement of the head, because that's really what we're talking about when we're talking about equilibrium. We're talking about where your head is, not necessarily the rest of your body, although we rely a lot on visual input in terms of balance, right? You can, it's much harder to balance with your eyes closed than it is with like a fixed point. And then also the proprioceptors, things like muscle spindles that are going to send that proprioceptive information to your cerebellum, so that your cerebellum kind of knows where you are in space as well. So if we look at our semicircular canals, the posterior one back here is what gets activated when you tilt your head kind of side to side. The lateral or horizontal semicircular canal really is what detects when you nod, or not nod, when you shake your head no, excuse me, and that kind of side to side. And then the anterior or superior semicircular canal gets activated when you nod, so up or down. And it's mostly about fluid movement, as we'll see in just a second. We're going to talk about static equilibrium first. And I think static equilibrium is really kind of neat, because I love how it gets activated. I love what the organs in the maculae look like. Essentially what you have are some hair cells, mechanoreceptor cells, that are going to connect to the vestibular nerve, that really are responding essentially to gravity, because what is laying on top of the stereocilia, on top of the hair cells, is this kind of gelatinous membrane, and embedded in this gelatinous membrane are these calcium carbonate crystals that we call otoliths. So yes, you have little tiny crystals in your ears, which I think is just incredibly nerdy and cool. You can see when your head is upright, gravity is pulling down directly on the otolith crystals. And so the stereocilia aren't really being bent in any direction. And so we get kind of just a steady kind of mid-range frequency of action potentials. And so that gets sent to the vestibular nerve, which then merges with the cochlear nerve to become the vestibulocochlear nerve to go into your brain. And your brain can then interpret that information as, hey, my head is upright. But then if you bend your head, as you see in either of these instances, if you tilt it forward, then the otoliths are responding to gravity, and they bend the stereocilia one way, and we get lots of action potentials, very high frequency action potentials, because the hair cells are depolarized. Lots of neurotransmitter being released from the hair cells onto the vestibular nerve, and your brain is then able to interpret that as you've bent your head forward. If you bend your head backwards, you do a little hyperextension there, then the hair cells bend in a different direction, or the stereocilia bend in a different direction. The hair cells then hyperpolarize, release less neurotransmitters to the vestibular nerve, and we get a decrease in the frequency of the action potentials in the nerve. And your brain can then interpret that as, hey, I'm bending my head backwards. So it's really all about gravity, and how these otolith crystals are responding to the pull of gravity. Now, if we look at the ampulla inside the semicircular canals, this is all about what we call dynamic equilibrium, the movement of your head, not just the position of your head. Is it bent forward? Is it upright? Is it bent backwards? But how are you moving? How is your head moving? How is your body moving? So you can see when we're at rest, the ampullaris with this little cupola kind of casing over it is upright. And the stereocilia, the mechanoreceptors, are not bent. But when you move, then we get this flow of fluid, this kind of movement of the fluid inside the semicircular canals, which then bends the stereocilia a certain direction. And then your brain is then able to interpret that. When the stereocilia bend, the hair cells inside the ampulla release neurotransmitter to the vestibular nerve, and we get an action potential saying, hey, I'm moving. So it's really interesting, I think, anyway. How it's all about the movement of fluid, and the movement of fluid inside the semicircular canals, that is really responsible for that, what we call dynamic equilibrium. How am I moving my head? Am I nodding it up and down? Am I moving it side to side, like like shaking my head no? Or am I bending it one way or the other? That kind of movement of your head is detected by the ampulla, which again are containing stereocilia, mechanoreceptors that bend when kind of deflected by fluid, which is very similar to what occurs in sound, right? The stereocilia bend and due to fluid waves. If we look at kind of the pathway for balance, again, eyesight is important. Photoreceptors talk not only to the cerebellum, but to the vestibular nuclei in your brainstem. That kind of alerts you to kind of where you are in the world. What are you staring at? That's why they always tell you if like you're nauseous on a boat or something, like stare at the horizon. It gives you a fixed point. We also get proprioception, so muscle spindles, kinesthetic receptors in our joints, tendon organs, receptors in our skin. They'll also kind of give us body position information. That information is also sent to the cerebellum and the brainstem, vestibular nuclei. Again, kind of where are we in the world? What is our body's position? And then the vestibular receptors in the vestibule and the semicircular canal are then giving us specifically head position and head movement, talking again to the brainstem and the cerebellum. And so really we have kind of three sources of information about kind of where we are in space in terms of how we balance. And then the vestibular nuclei talks to the cerebellum can talk to the vestibular nuclei and the brainstem, and then we kind of get our output. We get the cranial nerve 3, 4, and 6, which then allows us to direct our eyeballs to keep us kind of imbalanced. And then cranial nerve number 11 and the vestibulospinal tracts then allow us to move the head, the neck, the limbs, the trunk, again, to keep us balanced. And so it's really this combination of the vestibular receptors, the visual receptors, and these somatic receptors that talk to the cerebellum and the brainstem. They then also talk to each other. That results in the output of us being able to balance and not walk around like drunken sailors. So that is the end of chapter 15, the end of our special senses.